Sissies. Okay, so you get something that looks like that. All right? And by the way, your y squared over r squared is a very, very steep angle to see that expression. Can you see that angle? Okay. All those good genetics, eyesight. Okay, so now how are we evaluating this? One end, other, right? The other. So if this thing has a length of L, and I'm pointing from there, I'm going to go from whatever this distance is to this distance over here on this side. So L from one end to the other. If this is centered, life is good, because this is minus L over 2 in an x sense, and this is L over 2 in an x sense. Now, if it's anything else, then you just have to express this as a minus x max to a positive x max, if you will, minus x1 to positive x2, if you will. And we might just call this if we needed, or minus x initial to positive x, whatever you need to do to set those boundary conditions depending on where p is relative to the span of the wire. Just put those in there. So you guys all have these fancy calculators. And calculate what those values. Assuming you know how to use your calculator. And I'm going to throw a memory out here, and I'm probably going to be wrong, so if necessary, correct me. And I know you'd love to have me give you false information. I'll put it over here. So, based on this, the magnitude, or the field at any point P should be related to mu naught I y over 4 pi. And if this integral is something like, what is it? I think it's y squared over x squared plus y squared to the 1/2, square root. And that can't be a y, it's either an x or a 1. I'm thinking it's a 1. Double check, double check. You know, and if you're using your calculator, you're silly, just go to the front of the textbook. I think it's there, or the back of the textbook. You know those useful integrals I gave you on that last exam? It's actually there.
Or maybe I can break this 240.
I know, you probably didn't even crack it open. I don't need to use that. I don't need to calculate that. I do
Yeah,
not know how the hell to
it's,
calculate an electric field in a cylinder. But, hell with that, I ain't going to calculate that integral.
The only thing that you're missing
What am I missing here?
is that it should be an x instead of a 1 in the numerator there.
It is a 1, or an x. Like I said, I was either an x or not. There. Okay. I had a feeling it was a 1 or an x. I knew it, so I asked to check. Thank you.
Well, got my calculator out and everything.
Did it do that, by the way? Did it get you there? Now, y is a constant. We can put a value in for y, but... And the direction of this thing? In this case, since I already know the cross product E business, this is going to be in the positive k direction, I'm pretty sure. Well, this is not fun by any stretch, but... Acquired taste. It's like a fine candy.
It's like a fine.
It's like fava beans and a nice candy. Some duct tape. Okay, so we get mu naught I. One of these y's goes away. And then we get in here. Nice thing about that x squared and these being symmetric is whatever that is going to stay. So I'm going to have x squared plus y squared to the 1/2. And I'm left with L over 2 minus L over 2 in the k direction. So having squares in your limits of integration with symmetric limits is nice.
And we're calculating the total magnetic field.
Yeah. This would be B vector. The magnitude would just be the magnitude the same without direction. But calculate direction, we do this. And this x squared stops being x squared, right? It's going to be L squared over 2 squared. So how about 4? So what we are left with then is mu naught I, L over 2 plus L over 2 is going to give me an L over 4 pi y times the square root of L squared over 4 plus y squared. That would be the magnetic field due to this wire at any point above the wire, as long as we're looking from the center and not from one side of it. I know it's not pretty, so, but let's just think about some things. So, what is B when y is equal to .5 meters? And L is equal to 0.5 meters. What would be the field vector? Yes, sir.
Use of nine.
Do I leave out an X or do I read?
Let's do it. Or no, for that.
So, for this particular, for y equal 1/2 meter, BP would be related to, by the way, it's 4 pi times 10 to the negative 7th over 4 pi. So that really reduces to 1 times 10 to the negative 7th Tesla ampere meter. That's the mu part, mu for pi.
Use equal to-
And, oh, we gotta have a value for I, right? So how about 1 ampere, make our life easier. So now we have a current of 1 ampere, a length of wire of 0.5 meters, and a distance of, 4's go away, but I'm left with 0.5 times the square root of 0.5 meters squared over 4 plus 0.5 meters squared. I take the square root of all that, and that would be the k direction. So let's see, the amperes go away, the meters go away, and should there be a meter squared in? No, there shouldn't be a meter squared. What's going on?
The 0.5.
Oh, this has a meter in it, right?
And that cancels the 0.5 at the top.
No, it doesn't. What about this one then?
On the top, that's
What's that?
L over Y, so that cancels.
So because x, as you're evaluating the integral, x goes from minus L over 2 to L over 2. So for either case, x squared is going to be L over 2 squared. So x squared, the magnitude is going to be L over 2 quantity squared. Because I'm in max, in the limits, I'm in L over 2 on either side, plus or minus. I jumped it. That was totally good. Now I can't go back. So, as I'm looking at it, I'm not happy with something because my units don't seem to be right. There's something going on here and I don't see it, but seriously,
Okay,
So,
so you're ending up with a meter squared.
no, I'm ending up with a meter squared, and that's clearly not, magnetic field's gonna be in Tesla, not in Tesla over meter squared, so what's going on here? Did I leave something out? Amperes, Tesla meters. I clearly left something out because I look at it, this cancels out. All the L's cancel out. These cancel, the M's cancel, and the amperes cancel. So what's the matter with this? I've got my mu naught, I've got my I, and I've got my L. I've got my Y, and I've got all of this stuff. Why does this not cancel out over there? Come on, Ian, what's going on here, man? You're my unit guy. I rely on you. Seriously, I don't see it. I just plugged the numbers in there. Are these not the right units for Tesla from Unite? Should be. Is it Tesla meters?
well, let's just run a moon out here and know exactly.
If it's Tesla meters, Tesla meters? Is that what it is? Now they cancel out.
Well, you still have a meter in that. They have Tesla per
So
meter.
that would get rid of that one, and this would get rid of this one. So that's consistent now.
Oh, I see.
Yeah, so it has to be. When in doubt, write it out, right?
So,
That's what we use for,
So then this gives us basically the 0.5s in this case cancel out, which is nice. So I'm left basically with
meters over here.
1 times 10 to the negative 7th. The meters are all going to cancel out. So I'm going to have Tesla over the square root of 0.25 times 4, or divided by 4, which is going to be 1/16.
yeah,
So I'm going to be left with 1/16 plus 1/4, which would be 4/16. At least I can get that 16 out of there. This is in the K direction. I don't know what that number is. I'm just trying to make as much sense out of it as possible. So is this going to be something like 4 times 10 to the negative 7 Tesla over the square root of 5? So a little more than 2. So it's going to be approximately 2 times 10 to the negative 7, give or take, a little bit less.
so what,
It equals our root 5 over 4.
Yeah. Root 5 over 4, which is about 4 on top of that.
Yeah.
Did it to you again, see? Half the time I'm right, the other half.
But then-
Okay.
I didn't see that 4 get pulled out.
Yes.
where'd the 4 pi go?
The 4 pi canceled out because this is 4 pi times 10 to the negative 7. And I divided it by 4 pi. So there's the trick. That's why it was expressed in terms of 4 pi. Kind of like 4 pi mu epsilon naught. Right? Because half the time the pi's come out of it. And you'll see where it comes from Ampere's law, why it's there. But, so this is going to be give or take a little bit less than 2 times 10 to the negative 7 Tesla. So, and that would be in the K direction. So, when we take a break then, we're looking at this calculation. Let's look at 2 different Y's. 2 other different Y's. And want to get a sense of this calculation. Write every step out, don't redo it, or don't just re-plug in a new number in the calculator. So, what is B P when y is 0.05 meters and L is 0.5 meters? And when y is 5 meters, or 0.5 meters, excuse me, and L is 0.05. We got two cases here. We got one case where L is really long, really large compared to Y. This is basically a very long wire, and P is somewhere like this. In the other case is we have a very short wire, and P is really large. So what are these B fields? It's okay as long as you remember how you get to it. Try not to use the class as a vehicle for calculus per se, but there are a few places where it's helpful and necessary, and constructive to go through it. What does this do for us? Same eight, yeah, just keep life easy.
That's where that, I thought it was a four, what was I doing?
400.
Wrong.
Okay, I needed to know this.
3.9, so we got.
Okay, so for these values of L and Y, this corresponds to, give or take, 0.5 squared over 4.
2.
So BP, this tells me with this that this is going to be approximately U naught I L over 4 pi Y L over 2 in the K direction. That 2. This breaks down to about mu naught I over 2 pi Y. For these sets of values. So, I don't know what this comes out to. this is basically 2 times 10 to the negative 7 divided by 0.05. Which would be 5/500ths. So 2 times 10 to the negative 5th over 5 Tesla in the K direction, or 0.4 times 10 to the 5, or 4 times 10 to the negative 6 Tesla. That's all right.
That's what I've got. Well,
Good.
using the rigorous calculation, not much different from that.
Yep, exactly.
Just wanted to double check that.
Very good, Rob.
Now, so if you did the calculation, I approximated, I just said these are about this. If you do it a long way, what do you get?
3.92 times 10 to the negative 6.
Pretty close.
Okay, so moral of the story. When L is much larger, or I'm sorry, when L is much larger than Y, the L term dominates, because you have to add the squares. You can treat that in terms of just L and pull the L out. In which case, everything reduces to this. It's good to know. It's save your life trouble. You can always crank it into calculation, kind of like dipole moments and calculating fields of dipoles or potential of dipoles. You can always calculate it the long way. Never hurts. But just know that there is a simple way to do this. So when you're spending an hour and a half on a 1 hour exam just trying to crank the calculus and plugging all these numbers in, they're not making sense because you're plugging something wrong in your calculator. You just know that sometimes you can simplify it. Now the other case is when Y is much larger than L, it starts looking like a point, not a point charge, but like a bar magnet, a point magnet, if you will. So for the second one, dt should look something like mu naught I L over 4 pi y square root of y squared. Or mu naught I L over 4 pi y squared. What does this look like?
No, it's the.
One y comes out.
Oh, yeah.
If you notice, this was kind of our definition of our IDS. But when L is small, ds is basically L. This is like a point charge. Now it looks like a Coulomb's law relationship. If your IL is your movement charge element and it's like a point, close enough relative to y squared. Right? Everything, when you look far enough away, it looks like a point charge, if you will. Well, even magnetic fields for wires over long, long distances look like point magnets, if you will. So we could plug the numbers in here, and basically be 1 times 10 to the negative 7. And the L in this case was 0.05, so this would be 5 times 10 to the negative 9 divided by y squared, which would be divided by a fourth. So 2 times 10 to the negative 8 Tesla.
Yeah, well, what I got was 1.99, so.
Okay. So write that down. When you have a straight wire, it reduces to something that looks like a point charge when you have a very short L relative to your Y. In other words, if I took my sensor out here and I tried to measure the magnetic field due to the due to the charge, the current that's flowing through a fluorescent light. As long as I'm far enough away, that starts just looking like a simple point magnet, if you will. On the other hand, if I'm really, really close, it starts looking like a wire that is the length of which completely dominates that calculation for the most part. Which forces the L out of the calculation altogether, and it's inversely related to line. It's like a line of charge. Okay, so this is completely analogous with this model. It doesn't look like it to everything we did with electric fields, only you replace Q with IDS. So make note of that. It actually reduces to everything we've done before, but it does require the familiarity of remembering what we did before. You don't have to, you just crank it out unto itself, but it's everything we've done before. Again, physicists are not original. They were, they shave their beard and reform it once in a while, comb their hair, go away. They usually don't. Not very original. Okay, so let's take a break. I'll show you a simple way to calculate at least one of these cases, which leads to a fundamental law of nature called Ampere's law. Oops.